Welcome back to Science Click. Today, what would we see if we fell into a black hole? A black hole is a spherical region of the universe, a sort of space-time bubble which has an intense gravity. This bubble attracts objects as if it were pulling the fabric of space, not unlike a star or a planet. The surface of the bubble is called the horizon of the black hole. It divides the universe into two regions, the exterior and the interior. Below the horizon, the fabric of the universe is pulled so quickly that nothing, not even light, can escape. Today we know that our universe contains many black holes. They are very distant and represent no danger to us. Nonetheless, we can wonder out of curiosity what we might see if we were to fall into one of them. Answering this will allow us to improve our understanding of the extreme phenomena of our universe, and to rectify a few common misconceptions on the subject. Our galaxy, the Milky Way, hosts in its core a supermassive black hole called Sagittarius A star. Using a spaceship, we approach it at a reasonable distance, and we jump into the void of space. Here begins our fall. It will last about 1 hour and will be fatal to us. The spaceship remains stationed, orbiting the black hole and witnessing our fall. Before we even start falling, we run into a problem. The black hole is supermassive. Its gravity equates to a mass millions of times greater than the Sun. With such an attraction, it captures stars and surrounding matter, forming a thick disk of plasma that orbits around it. This disk spins incredibly fast, almost at light speed, and loses energy by friction, causing turbulences that heat it up. It thus produces intense radiations, light, ultraviolets, X-rays and gamma rays, which blind us instantly and risk burning us alive. The plasma itself, which can reach several billion degrees, might also well burn us alive. In what follows, we will therefore assume that we are equipped with an extremely resistant spacesuit, which allows us to withstand the heat and filter out any harmful radiation. However, despite the spacesuit, the disk still seems extremely bright. We can't distinguish anything. We will therefore imagine that our helmet has a visor, which helps reduce the brightness of the disk so that we can observe it in detail, as well as see the stars in the background. At first, we notice that the disk is blue. Within the whole electromagnetic spectrum produced, our visor filters everything but visible light, the light our eyes can see. In this spectrum, the disk emits more blue because this colour is more energetic. It is the same effect that gives very hot stars a bluish tint. Strangely, one side of the disk looks brighter than the other. To understand, the matter orbits very quickly, such that on one side it approaches us at high speed, while on the other side it moves away. On one side, the light waves get stacked together, we receive them with greater frequency, while on the other side the light gets stretched, we receive it with less energy. This is called the Doppler effect. It's the same phenomenon that occurs with sound waves when a car crosses the street. Looking at the black hole, we see that the back of the disk appears warped, as if it were folded around the horizon, forming a ring of light. This is due to the strong gravity of the black hole, which deflects light rays, acting like a gravitational lens. Looking in one direction, we observe objects that are actually located elsewhere. Finally, the stars in the background seem ever so slightly blue. We do not feel it, but the black hole distorts time, such that our clock turns slightly slower than that of distant stars. Compared to our clock, the light from the stars seems accelerated, to the extent that we see it bluer than its original colour. Surprisingly, during the first 10 minutes of the fall, the black hole appears to be moving away. We are moving closer and closer to it, but its image seems to shrink more and more. Imagine throwing a ball through a car. The ball is thrown at 90 degrees and crosses the car side to side. The passenger sees the ball travel across the car at 90 degrees. But imagine now that the car is moving. This time, the passenger sees the ball coming from the front with a narrower angle. Because the car is moving, objects reaching it seem to come from a different direction, more from the front. In our case, the situation is analogous, only with light rays instead of a ball. We receive the light of the disk from a certain direction, but because we are moving towards the black hole, the rays seem to reach us from a different direction, squashed towards the front. This is called aberration. After these first 10 minutes, we are now falling very quickly, at 4% the speed of light. And from this point onwards, the black hole starts to grow in our field of view. As minutes go by, we gradually descend towards the black hole. Our speed increases and we receive the light in front of us with an increasingly high intensity, while the light behind us seems to get darker. This again is the Doppler effect at play. When falling towards the black hole, we catch up with the light in front of us, while the light behind us has more difficulty reaching us. If we turned around, we would notice that the clock inside the spaceship seems to be running slower than before. The effect is subtle, but still noticeable. This is also due to the Doppler effect. If we imagine that the clock emits a signal each second, these signals take longer and longer to reach us, and we thus observe the ticking in slow motion. Minutes pass, and we gradually fly over the disk of matter. Suddenly, after 57 minutes of falling, the disk seems to fade out. We have just reached the point beyond which matter can no longer orbit the black hole steadily. The gravity is so intense that at this distance, the plasma begins to spiral very quickly into the black hole. Things will now get much faster. Just 2 minutes later, we are twice as close to the horizon. From now on, any light coming from outside is destined to fall into the black hole. This is called the photon sphere. At this precise distance, it's even possible for light to orbit the black hole. As we approach more and more, the passengers who remained in the spaceship see our image fade and gradually slow down until freezing on the horizon. The light that we emit takes more and more time to escape the black hole. It is received increasingly slowly and gradually fades away. The passengers will never see us cross the horizon. But for us, just 24 seconds after crossing the photon sphere, it is time to reach the horizon. After this moment, it will be impossible for us to go back. But what do we see when crossing the horizon? Surprisingly enough, nothing special. It would in fact be very difficult to determine when exactly we cross the horizon. We still receive the light of distant stars, which falls with us. We can still see the spaceship in orbit, in which the clock, even if it seems slowed down, is still ticking. And we can still perfectly see our body and in particular our feet, because even if all light is carried inwards, it can still move upwards relative to us and thus reach our eyes. This is actually a fundamental principle. On a global scale, space-time is curved by the black hole and generates this horizon inside which objects are disconnected from the outside. But at the local scale, space-time is almost flat and the curvature is not noticeable, which means that everything behaves normally. Furthermore, as opposed to what one might think, the image of the black hole does not appear to encompass us at all. Even if we are now inside the black hole, its image only takes up 15% of our field of view. The rest is still filled with stars. This is again due to the phenomenon of aberration. Now that we move extremely fast, the light that arrives from the sides and even from behind seems to come from the front. Our field of view is contracted ahead of us and widened behind us. In particular, the spaceship behind us seems to grow larger, even though we move away from it. We have crossed the horizon and nothing special has happened. However, from now on, if we try to send a signal to the outside, it will never reach its destination. Below the horizon, everything is destined to fall downwards, with no hope of ever coming out. But for the moment, everything is fine. It is after another 30 seconds, just before reaching the center of the black hole, that in the blink of an eye we feel an incredibly powerful force that stretches us until dislocating our body. This is called spaghettification. Our head being further from the center than our feet, the difference in pull is such that our body is very quickly torn apart. In our very last moments, we have the impression of falling onto a flat surface, as if we were reaching the surface of an entirely black planet, while a circle of light intensifies all around us. A tenth of a second later, the shredded remains of our body reach the center of the black hole. Our journey ends here. For the moment, modern physics cannot describe what happens this close to the center of a black hole. Our current theories describe singularities, points where the curvature of space-time becomes infinite. But scientists suspect that these singularities do not really exist. We would have to unify gravity with quantum physics if we wish to understand these extreme regions of the cosmos. For now, some hypotheses even question the fact that one could survive crossing the horizon. Moreover, in reality, black holes can have an angular momentum, which generates strange effects with multiple horizons and mathematical instabilities whose consequences we do not yet understand. That said, our current theories still give us a good idea of what we would see. In particular, we can correct a few widespread misconceptions. For example, the disk around a black hole is not orange, but blue. If some images show it as orange, this is because they use false colours, which are only intended to represent luminosity, but not the real colour in visible light. Another idea that is widespread is that we would observe the whole history of the universe unfold before our eyes, while our field of view would get engulfed by the black hole. This is also wrong, as it forgets to take into account the Doppler effect and the aberration of light. There are, however, many mysteries left to solve, and we will have to wait until our theories are perfected to understand what truly happens at the heart of a real black hole.